Good evening and welcome back to Vegas October 1 Sounds. Tonight, this Napkin note will cover some of the very basics of gunshot acoustics. So let's start off by getting ourselves a badass assault rifle. There. And every time a round goes off from this rifle, we have hot gases escaping out the end of the rifle, and they create a sound because essentially they're the remnants of an explosion from the powder inside the round, and we call that sound a muzzle blast. And basically those expanding gases there form a bubble or a sphere, and that sphere expands out at the speed of sound until it's so big that it's no longer either audible or detectable. And it spreads out in all directions evenly, and we call that a point source. That is, the muzzle blast can be modeled as a point source. Now, technically and in great detail, the muzzle blast does have directional components. But for the purposes of the concept, we'll just consider it a point source. All right. Of course, the other thing that happens with that is that a bullet comes out of there and travels out for a while it travels in a semi-straight line, and then it begins to fall towards Earth because of gravity and slows down due to air resistance. And that bullet, almost in all rifles and almost all rounds, is traveling so fast that it's faster than the speed of sound. And if you've ever heard a sonic boom from a jet, the precise same thing happens with a bullet coming out of a rifle that's traveling, and when that bullet is traveling faster than the speed of sound, i.e. it's supersonic. Now, common bullets for a AR-15 which firing a 223 round quite easily can exceed 3,000 feet per second, and rarely fall under 1,800 or so. And given that the speed of sound in Vegas that evening was about 1,158, then these things are traveling somewhere between Mach 2 and Mach 3, or on the low end, maybe Mach 1.7. And just like a jet, as it travels, it creates little supersonic shock waves all along its path. And as long as that bullet remains supersonic, you'll get more and more supersonic shock waves, as we call them. So the bullet itself generates these sounds, billions of them, trillions of them, until it hits the ground, hits an object, or falls below the speed of sound, in which case there's no supersonic crack anymore. Now, together, all these multitudes of shock waves get together as they expand outward away from the trajectory of the bullet, and they form a cone. And I'll draw a cone here. This is a 2D representation, of course, of a 3D phenomena. All right. And that cone the leading edge of that cone is what we call the supersonic shock wavefront. And it travels is a bad word, it propagates at the speed of sound in the directions indicated by these red arrows. Okay, so we've got, for every round of a bullet that's fired out of that rifle, we've got essentially 4 events to consider. One is the muzzle blast, one is the bullet itself, that's the second one. The third one are the individual little shock waves, and the fifth one collectively is the cone formed by the individual shock waves that forms this supersonic shock wavefront. And the timing and geometry of all these things, i.e. when do we hear them, which direction do they go, blah blah blah, is all governed by, in the case of the shockwave, the geometry of this cone and the speed of the bullet and the speed of sound. And for the muzzle blast over here, it's pretty much just governed by the speed of sound, because it expands out in this sphere at the speed of sound, and just has to, travel a certain distance until it reaches a recorder or something. Whereas let's just draw it. So for the muzzle blast, we basically have concentric spheres, and on this 2D thing, it's concentric circles. And let's draw a number of them, and these circles represent where that sphere is at a given time. Okay, so at 1 unit of time, it's at the first one, 2nd unit of time, 3rd unit of time, whatever, and we can model this as anything we want. On the other hand, the leading edge of this cone travels in lines that are parallel. So at any point in time, it's traveled in the direction of the red line, but parallel to the cone. And the same thing is on the other side. And as you can see, this phenomena of the cone and the way that the front of the cone, not the front of, but the wavefront itself, are traveling in essentially straight lines. Much like you're at the beach and a wave comes in, it mostly comes in all at the same time, unless it doesn't, in which case, it's not. So we have to consider 2 types of propagation of sound here. And one is the circular or spherical motion of the muzzle blast, and the other is the linear or line propagation of the shock wave. And the 2 are substantially different in terms of time of arrival and characteristics. So let's get into some examples of the muzzle wave. So once again, if we have our gun, this time we'll put it right here, and we have the muzzle blast wave propagating outwards at the speed of sound. When will we hear that? Well, after we get done drawing it here, we'll put in a couple of observers and we'll ask that question. Now, for calculation purposes, I'm going to call the speed of sound, which I'll designate as c, to be equal to 1,000 feet per second. And that just makes all the calculations, doable without even thinking about them. In reality, the temperature, the altitude, the humidity, and a couple other things determine that speed. So anyway, so if this sphere is expanding at the rate of 1,000 feet per second, and each one of these is, let's say, 200 feet, let's call it 100 feet, then at the first red line, we're going to be 1/10 of a second after the gun is fired. The next one's going to be 2/10, 3/10, 4/10, 5/10, 6/10, and 7/10. So if we were to have an observer, let's say right here, then the path that the sound would travel would be from the source, which is the source of the gun, to the observer along this path. And that's an important concept. Sound always travels from its source to wherever it's being intercepted. And in this case, the source is the gun. So let's see, we have 1 line, 2 lines, 3 lines, 4 lines, 5 lines. So in this case, we be about 5.55 seconds, or 550 milliseconds. Okay, so that's one. So now let's take let's add 2 more observers and ask the same question. If I put an observer here, let's do yellow. Alright, and I put an observer over here. They're both, and then the sound would propagate from the source to the destination, or where it's intercepted, similarly above. Now, it's not to scale and all that, but in this case they're both the same distance from the tip of the gun, and so the muzzle wave would reach both of them at precisely the same time, even though they're on the opposite side of the sphere. And in this case, there's 7 circles, so both of them would hear the muzzle blast at 0.7 seconds. And this is sometimes a great point of confusion, because people often think that if you're on the ground and the source of the noise is elevated, that they can simply take the distance between the 2 people on the ground, divide it by the speed of sound, to determine when it should arrive after the first person. An example of this is, let's say that we have, in this example, even though it's kind of a top view, let's say we have a person at 1, 2, 3, 4, and then we have somebody out here. And let's go ahead and call the distance between the 2 of them about, it's not to scale obviously, but let's call it 600 feet. So now the question becomes, when does the observer here at A hear the muzzle blast, and when does the observer at B hear the muzzle blast? Okay, well, the correct thinking on this is that observer A hears the muzzle blast, which is the distance from the source to him divided by the speed of sound, and in this case it's 4 units, or 0.4 seconds. So A hears it at 0.4 seconds. Okay. And B hears it at, this is 7, 8, no, we'd have to provide some 9, 10, 11, somewhere on the order of 1.1 seconds. Alright. So the difference between those two is 7. So then you say, well, shouldn't that be equal to the distance between A and B divided by the speed of sound, which would net 600 feet over 1,000, or 0.6? And the answer is no, because the distance for the guy at B, their wave arriving, is this distance, which is approximately the sum of the squares of the distance from A to B and the distance from the source to A. But ignore that detail for the moment. The point is that without knowing where the source is, if you're on the ground and this position is elevated, you can't tell squat about the time of propagation between A and B, because sound doesn't propagate between A and B. It doesn't even travel from A to B, A and B. Now, if you know the geometry of these 3 points, you might be able to work backwards. But it's not even a really good approach. It's a bad approach. The question is, what time does it take for the wave to reach your position? And that time is the distance between the source and you divided by the speed of sound. And that is true for all points. It has nothing to do with the distance between you and another observer, except in some very special cases. And those special cases occur when, for example, let's start here and go backwards on a straight line. And we put two observers, one here and one there. So where all the observers and the muzzle blast occur on a straight line, either two-dimensionally or three-dimensionally, only in that case will the time between Z and Y, for example, divided by the speed of sound equal the difference in time of arrivals. So don't be confused by people saying that the speed of sound has been broken because the sound isn't heard. In the case of A and B, the distance divided by the speed of sound just doesn't work that way. All right. And in the simplest of cases, you can see it here with let's call these L and M, as we discussed earlier. They are 14 units across there. Divided by the speed of sound would be 1.4 seconds. Yet they both hear the sound at 0.7 because it's the distance between the source and the observer, not the distance between the two observers. Okay, that's for a spherical propagation. It's different for a linear propagation. So let's save this. And get our blank sheet back. Alright, so let's talk about linear propagation, which is more akin to what the supersonic shock wavefront does. It's that front edge of that cone. So in this case, let's say we've got a shock wave that's generated, and it's traveling X number of feet per unit of time. Now, it's interesting to note, okay, and let's just call this time 0. And again, we're going with the 1,000 feet per unit of time. 1,000 feet per second for the speed of sound. And these are all 100 feet apart. So, that's 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6 in terms of the time of arrival of this supersonic shock wavefront. And if you want to, toss in the bullet here, the bullet trajectory, that, adds a little reality to it. Okay, so place an observer somewhere. Then let's place one right along this edge. When does the shock wave reach them? Well, in this example, it doesn't start at 0 because the shock wave that's here was created earlier. That is, we have to draw in a few more lines here because it's created by the bullet, so it has to originate on the bullet path. Okay, so what we would do is draw a line perpendicular to our position that intercepts the bullet. And at that point is where we start counting. So in this case would be 1, 2, 3, 4, 5, 6, 7, 8 units of time, or 0.8 seconds. Okay. So let's put somebody anybody along that line is going to intercept the same shock wavefront, just at a different time. But what if we put a person let's say here? Okay. Well, they're on this line, aren't they? Yeah, so naturally you would think that they hear or intercept these supersonic shock wavefronts at the same time. And they do, but they don't hear the same one, because, as is usual, the sound we hear is perpendicular to that wavefront, because that's the shortest path. So in this case, this spot would be where that supersonic shock wave originated, and it would be 1, 2, 3, 4, 5, 6. So for location B, location A, we have this is A, this is B, and B is heard at 0.6 seconds relative to when the bullet leaves the trajectory. The other thing you have to consider is how long the bullet was traveling. So in the case of B, it was traveling there, and in the case of A, it was traveling here. So to get the total time for A, so the time of arrival of the shock wave for A then would be equal to this distance up there, which we'll call A prime, over the speed of the bullet, because after all it's the bullet speed we're talking about along that path, plus the time along this path, which would be the distance, 1 unit, 2 unit, 3 unit, 4 unit, 5 unit, 6 unit, 7, 8 units. 8 units over the speed of sound over c, which is 1,000 feet per second. And similarly, B would be however long it took B prime, which is going to be substantially longer than A prime. Over the speed of the bullet, plus the time it takes to propagate from where where the shock wave left the trajectory to the location, which would be 1, 2, 3, 4, 5, 6. 6 over the speed of sound. So as you can see, the time of arrival of these lines, while they're all parallel, is dependent upon two factors. One is the path that it takes that shock wave leaving the trajectory of the bullet to arrive at B, plus the time it takes the bullet to get to that point. And these paths here are traveling at the speed of sound. Okay. And these paths are traveling at the speed of the bullet. And that's the basic fundamental timing of the supersonic shock wave. But let's review that in a different way. So, if we've got a gun and it fires a bullet, okay, and we have an observer out here somewhere, then when does the shock wave arrive there from the bullet? Well, the bullet travels along a certain distance until the shock wave leaves the bullet. The bullet keeps on doing its thing and propagates to the observer. So if we call this A, the length of that line A, and the length of this line B, okay, then the time of arrival is given by A, the length of A, over the speed of the bullet, because it's the bullet that's traveling there, or the velocity of the bullet, plus the time of the shock wave, which propagates at the speed of sound to the observer once it leaves the trajectory of the bullet, B, plus over the speed of sound, excuse me. Okay, and so that's the basic concept of the shock wave for a supersonic bullet. It's a cone. It propagates in a linear fashion, and the time of arrival is a combination of the distance the bullet travels and the distance that the shock wave travels, not the supersonic shock wave front, but the shock wave. So you can see that the time of arrival is a function of both, if you want to put it in terms of this point right here, of the downrange distance, which is that distance parallel to the travel of the trajectory of the bullet, and this distance. And this distance we call cross range or miss distance. And this one we call downrange distance. Okay, so the arrival time of the shock wave created by a supersonic bullet is a function of the distance that the bullet travels before that shock wave generated at that point departs from the bullet and travels at the speed of sound to the observer. Okay, and you can express that in terms of the downrange distance and the cross-range distance. And then you have to know the speed of the bullet and the speed of sound to make the calculation complete. So let's talk about some examples of this shock wave. Okay. And once again, if we have the bullet trajectory, just going to leave it as a straight line this time because it's a whole lot easier. And I'm going to put several observers on this map, and we're going to talk about them. Alright, so the bullet is traveling in this direction. And of course we've got our gun here. And of course there's a shock, there's a muzzle blast coming out there, but we've kind of been ignoring it for the last few minutes. But we're really talking about now the shock wave created by the supersonic bullet. And before we go any further, let's talk about this somewhat in terms of general observations. If the bullet is generating all these individual little shock waves, which collectively form a cone and collectively generate that linearly traveling shock cone wavefront, okay, then a shock wave generated here has an existence separate from the bullet once it's generated. That is, once the bullet generates that sound and it starts making its usual little circular motions there, which add up to a piece of the cone, it's going to continue to do that regardless of what the bullet does. So if the bullet were to hit somebody at, say, this point, you'd still hear all the sound from all the supersonic shocks prior to it. So the bullet has a life of its own, and the supersonic crack has a life of its own once it's generated, and they're independent. And of course, obviously, the muzzle, has a life of its own. Now, once the bullet stops generating these cracks, then this wavefront here stops being linear and just goes back to being completely spherical in nature. But anyway, so let's talk about this. So let's give them numbers A, B, C and D, letters. I guess those aren't numbers. For A, we're really close to the trajectory of the bullet. And so the propagation time between the path and our position for the shock wave is itsy bitsy. Similarly for B, itsy bitsy. And since it's so small, we can essentially ignore it. So the arrival time of the shock wave, which is a combination of the time it takes the bullet to get to that point, plus the travel time of the shock wave itself, boils down to nothing more than the distance between the rifle and the point where it leaves it, which we'll call x1. And so the arrival time of both B and A, since they're on the same equal distance from the line, the arrival time of them, so arrival time of that for the shock wave becomes simply x1 over the velocity of the bullet, presuming the velocity of the bullet is constant, which for less than 400 yards for a 55 grain .223 round is pretty valid. Once you get past that, it's going to start slowing down and things change. We'll just leave it at that for the moment. So from this we observe then that if the position we're at is close to the trajectory of the bullet, then the calculating the arrival time of that shockwave becomes a very simple process of taking the distance between our position and the gun and divided it by the speed of the bullet. There's another simple case, and that simple case is one of the simple cases is at C. In this case, the shock wave that we hear is generated right in here. So I'll choose a different color. Let's choose dark blue. No, I don't want dark blue. Let's choose white. In this case, the shock wave is generated right in there and propagates all this distance, which was quite long. And the muzzle, so in this case, the travel time for the bullet is really short, and the travel time for the sonic shock wave at the speed of sound is long. So in this case, we can say that the time of arrival of the shock wave is approximately this distance, which we'll call C prime, over the speed of sound. And those are two cases where it's fairly easy to calculate. So you can see that for one bullet and two different positions, we have completely different times of arrival for the shock wave. And that's what makes it so interesting, is that it's hard to predict where this shock wave is going to, or how long it takes to arrive at your location, unless you know a lot of parameters. You have to know approximately where the gun is, you have to know where the bullet path is, because if we fired another bullet and everything else stayed the same, if we fired a bullet and went off this direction, then nobody's near the bullet trajectory, and they all have long propagation times for the shock wave. And it would even be hard for me to predict where the shock waves would be, but I think that's about right. So you can see that just by changing the trajectory of the bullet, the entire times of arrival for all observers changes. And that's what's happening in Vegas, is that these bullets aren't traveling the same path every time, and because they aren't, the shock waves, the snaps, arrive at different times. Alright, let's save that. And let's wrap up this note, because it's getting kind of complicated. And let's go back to some other simple examples on the next notebook. So for this evening, that's a wrap. We'll grab you in the next one.